Hello. Let everyone join. We'll be waiting for 5 minutes and then we will begin our session today. So Today we are live on YouTube also. One can join through YouTube or one can join to our Google Meet also. So in both ways we will be interacting with the participants. On YouTube we have already 10 people who have joined. Let's wait till 11:05 and then we will be beginning our session today. So let's wait for others to join, and meanwhile we'll be introducing you to our platform through which we provide the knowledge sharing sessions. So the first platform that we are using, that is our YouTube channel, which is for everyone. Anyone can watch our videos, our sessions. We used to upload a few of our paid sessions also to the YouTube channel so that people can get the best out of it. So you can see this is our YouTube channel. We have more than 100 videos till now, including the different software applications, the theoretical concepts. So you can always refer our YouTube videos for that purpose, for your learning purpose. And then we have our Android and iOS based platform, which is all of you know, which is the Ilustraca Academy app. So in the Ilustraca Academy app, it is available in the Google Play Store, and those who are using iOS, that means iPhone or any iOS device, you can also access our platform through My Institute application. So from the App Store you can download the My application. Just give me 1 second. Yeah. So as this, okay, so from the my app store you can download the My Institute application, and it will ask you for the organization code, where you have to just put AMITCO. Okay, the organization code for us is the AMITCO, Amitco. So you will be redirected to our platform, and you can see what are the contents available here. So the content that I was talking about yesterday was this one, the advanced study in RCC building design using ETABS and manual checks. So whatever we are explaining in these sessions, these things are again explained in this courses in detail. So if you see the contents, all the codes, the lecture documents that we are using, reference books, ETABS files, whichever file we are using, the project reference files, and different projects that we are doing in this course. So here you can see, I think I have not shared the screen in Google Meet. Just give me 1 second. Yeah, so you can see the contents available in this particular course. So till now we have 40 videos, 40 lectures, and it is actually ongoing course, so we are uploading every week, so you can have a look on it. And we too have other different courses also. For site engineering, we have the site engineers course, we have the interview preparation course, okay, we have bridge engineering course. These courses are not available till now, so we have just published this. So we have the stat pro course, and it will be same kind of explanation will be there as we have in the ETABS. So all the manual calculations and proof checks will be doing. Okay, so these are the two platforms we are using for knowledge sharing. One is our YouTube and our Android and iOS based application, which you can check for your reference. Okay, so let's not waste more time of you. Let's begin our today's session. So the topic for today's session, let me see if I have, okay, so the topic for today's session is column design, RCC column design using manual method or using the software. So first of all, as we have seen in the previous session, we have done the manual process first, and then accordingly we will be checking how the software is giving us the output. Okay, and we will you can say we will recheck whether those values or those answers that we are getting from the softwares like ETABS and StatPro are genuine or not. Okay, so let me open the whiteboard. I hope the whiteboard is clear to all of you. So okay, Rahul is saying how to join from Google Meet. Okay, let me just share the link. Actually, those who have joined through YouTube, they were asking how to join through Google Meet. So I think I have shared the link, Rahul. So one who want to join through our Google Meet, you can join from here actually. Okay, so fine. Now so as I was saying that whenever you have any doubt, please do write in the chat box. I'm using only one screen, so I'll not be able to see those I can say your questions during the session. So in between we'll be taking some break for your question answer, and then I will answer those questions. Okay, and again, if it is very important, you can always unmute yourself and you can ask the questions. Okay, so here in column design, the first thing that we have to understand is, suppose let me draw a cross section like this. Okay, so this is the cross section of column, and suppose these are the major and minor axes of the column. So I'll just ask you guys one question, that can you tell me which one is the major axis and which one is the minor axis of this particular column? So we have x-axis and we have y axis. So I just want to know that if you can tell me which one is the major axis and which one is the minor axis for this particular column. So I have got one answer, which is x-axis. Let me see in YouTube whether they have any answer for this. Anyone? Yes. So it is correct actually. Xx is the major axis and yy is the minor axis. So the basic funda to understand this thing is, if you see, when we have column, suppose this is my column, okay, and we are having the you can say axial load or vertical load on it, and obviously we will be having moments in it, right? So maybe suppose the moment is about this direction, and here it is about this direction. Okay, so we have pu, we have suppose mxx, and we have myy. So mxx and myy. Now if you if you can see that which particular dimension of this particular this column will provide more resistance to the moments. So obviously, as the material distribution is higher in this particular dimension, suppose this is my depth and this is my width of the column. Okay, so obviously in this, about this particular axis, we'll be having more resistance for the to the moments. So the moment of resistance will be higher in this particular direction, right? So about x-axis, because the column, if it is sway like this, so suppose this is my axis, which is x-axis, so this is my mxx. So the moment of resistance about this axis will be higher if this is my depth. As in case of the width, it can be something like this. Okay, so the dimension is smaller here, so obviously it cannot provide more resistance than the first case, right? So now if you see, we have three conditions. One is pu, one is mxs, and one is myy. So if I draw a section, and if I draw the lines also here, the axis, and let me divide this axis to 1, 2, 3 and 4 quadrants. Now tell me, we have pu, we have myy, we have mxx. So in the first case, what are the conditions we will be having in terms of compression, tension and compression, if you say? So due to pu, we will be having compression in all the 4 quadrants, right? So I will write it here: 1, 2, 3 and 4. So due to pu, we will be having compression here, 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 right? Now what about mxx? What about mxx? Due to mxx, where we will be getting the compression and where we will be getting the tension? Can anyone tell me? Can anyone tell me where we will be getting compression and where we will be getting tension due to MXX? So yes. So I was talking about actually MXX. So it will not be left or right, it will be top and bottom if you see. So here, yeah, for 3 and 4, if you just tell me about using these numbers. So in 3 and 4, we will be having tension if you see this MXX direction. So 3 and 4, we will be having tension. And 1 and 2, this 1 and 2 will be having compression, right? Now again, if I talk about MYY, in that case, what will happen? See, 1 and 2 will be under tension because the direction is in this direction, right? 1 and 2 will be under tension, and 2 and 4, sorry, 1 and 3 will be under tension, and 2 and 4 will be under compression. Right or wrong? Okay, I hope it is clear. So yeah, anyone have any question? Yeah, okay. So because if you see the direction of the moment, you just see the direction of the moment, it is coming like this. So here it is making tension, here it is making compression. Due to this, it is like this. So here it is making tension and it is compression. And as PU is acting here, so it will give compression to all the 4 quadrants, right? So now if you see that in many cases, there are 3 cases that we know about column design, which is axially loaded column. So there only we will be designing for PU. Uniaxial loaded column, so it will be PU plus MXX or PU plus MYY, or biaxially loaded column, so PU plus MXX plus MYY. Now in real scenario, if you see, there will be hardly any column exists with these 2 conditions. You may assume that is different. You may assume a column as axially loaded or uniaxially loaded, but there is hardly any situation where you will find these 2 exactly happening. Okay, so most of the cases you will see that the columns are you can say subjected to compression due to the PU, that means the axial load, and the biaxial moments, so moment about x-axis and moment about y-axis. Okay, so today our discussion will be based on this particular concept, that a biaxial design of the column. Okay, so now we will go step by step the process for column design. Okay, so the first thing that we will be needing to design a column is these 3 things. One is, so the inputs we need, right? So design inputs we need. So inputs. So the first thing we need is PU, analysis moment about x-axis, and analysis moment about y-axis, right? So these are the 3 inputs we will be needing. So from where we will be getting these inputs? See, as I am saying it very clearly, nowadays we hardly use any manual process or manual method to go for you can say analyzing the structures, because we have complex structures. Even it is a simple frame, still we use the softwares like StatPro or ETABS to create that frame and analyze it, right? So these analysis results we can directly get from the will be getting from the software itself. Okay, so for which load combination we'll be getting these values? So obviously we'll be getting these values for the factored load combinations, and whichever is giving the critical condition, will be taking the values from there, right? So in case of column design, you cannot take any envelope case, but because the problem is we'll be creating the interaction diagram for every combination. Okay, so because in column we have this interaction concept, so we need to interact, or we need to see how the column is behaving under different combinations of PU, MX and MY. Okay, from there we'll be finding out the capacity. It's not like beam design. In beam you can create the envelope and you can see the maximum PU, maximum MX and maximum MY. Taking those values you can design the beam, that will be fine. But in column it's different. Okay, in column it's different. We need to check the interaction for every single combination. Fine. So now suppose we are getting these inputs from the software, and then the second case, now these things we need to do by ourselves. Obviously softwares are doing, but we need to understand these things. So the second case is minimum eccentricity. Okay, the second case is minimum eccentricity. So what is this minimum eccentricity? Suppose we have some column like this, okay, and we are expecting that the beam should be like this. Sorry, right? But in construction site or for any other reason, it can be like this. Or if I draw from the cross-sectional view from the top, so the beam can rest somewhere here. Right, so we will get, this is the top view actually. Okay, this is the top view, not this, not the top view of this particular thing. I'm just saying we can have this kind of situation where the beam is you can say not here actually. Let me draw it properly. Beam is somewhere here, resting somewhere here. So here we have the center line of the column and beam is somewhat shifted, and here in this case it is also the similar kind of thing. So the beam is resting somewhere here, not at the center. So what will happen? We may get some eccentricity, a moment due to this distance. Suppose this distance is E. So due to this eccentricity, we will be getting some moment, right? So this moment due to the eccentric loading, we call it as, you can say, there is some limitation for which we need to design the column. Okay, there is some criteria for which we need to design the column. So this particular thing we need to find out as per the codal provision. So this is called the minimum eccentricity. Even though we do not have any such condition, still you have to check the column for the minimum eccentricity value. So what code says about it, that if you just open the code and if I go to page number 42, yes, page number 42, 25.4 clause. So here you can see the code says that all columns shall be designed for minimum eccentricity equal to the unsupported length of column divided by 500 plus lateral dimension divided by 30. So L by 500 plus D or B by 30. Okay, so let me explain this thing. So what is this unsupported length? What is this unsupported length? So if I draw the column, suppose this is my column and these are my beams. Okay, these are my beams. So from the top of the beam, to the bottom of the top beam is called my L unsupported. L unsupported. So this is my center, suppose. Okay, this is my center. So from top of the bottom beam, that means the floor level, to the bottom of the top beam, we call this length as our unsupported length. So the minimum eccentricity that we need to consider, so minimum eccentricity, it will be L unsupported by 500 plus. Now we need to check minimum eccentricity for both direction one by one. So suppose this is my column, and here we have suppose 1 1 and 2 2 axis. So about 1 1 axis we need to check, and about 2 2 axis we need to check individually. Okay, so about 1 1 axis it is my depth, about 2 2 axis it is my width, right? So for 1 1 axis it will be d by 30, and again 2 2 axis you need to check whether there is any beam or there is any support. So accordingly you need to find out the L unsupported, and for 2 2 axis it will be the same. L unsupported means the unsupported length. Obviously it can be different from the first case, so you need to check what is the L unsupported divided by 500 plus, now as it is about 2 2 axis, so it will be b by 30. Okay, so we will get some eccentricity value, suppose E1 and E2. So we got eccentricity. Now how will we be finding out the eccentricity moment or moment due to eccentricity? So the moment due to eccentricity, suppose ME1 equal to whatever axial load you are getting, so PU multiplied by the eccentricity. Load multiplied by eccentricity, you will get the moment, or load into distance, you will be getting the moment. So PU multiplied by E1 or ME2 will be PU multiplied by E2. That will give you the minimum eccentricity. Okay, now when you will be designing the column, you need to check what is the minimum eccentricity value for both the axes and what is the analysis moment for both the axes. So okay, so whichever is higher for each direction, one by one you need to check. Suppose we have MXX and we have MEX or E1. Okay, let me change this concept from MXX to M11 so that it will be easy for us to actually discuss as per our software annotation. Okay, so let me take it to make it M11, M22. Okay, so we got suppose M11 and we got the moment due to eccentricity ME1. Again we got M22 and moment due to eccentricity ME22. Now whichever is greater from these two, will be taking the greater one, and whichever is greater from these two will be taking the greater one. Okay, it's not like we'll be taking the both. We'll be taking the greater value of the analysis moment and the minimum eccentricity, moment due to the minimum eccentricity. Whichever is greater, we'll be taking that, and we will proceed for the designing. Fine. So we will not use the both. We'll be taking one in among the analysis moment and the minimum eccentricity moment. I hope it is clear. The minimum eccentricity thing. Okay. So then the third thing. What is the third thing? Suppose we have a column like this, and we have a column like this. Yeah, anyone have any question regarding this? Any question? Okay. Yeah, we will discuss this. Just wait for it. We have just started. Okay. So we have these two columns where the L of this particular column, suppose L1, and L of this particular column, suppose L2. So L2 is much greater than my L1. Now here this PU is acting, suppose. Okay. So obviously we know that due to the axial load, we will have some lateral, we have some flexural buckling of the column, right? So there will be some flexural buckling of the column, something like this, and something like this. Now you can easily understand that whenever the length of the column, the unsupported length of the column or the effective length of the column is higher, in such cases, the chance of having this chance of having this flexural buckling, higher value of flexural buckling is more, right? So due to this flexural buckling, or due to this kind of behavior, what will happen? Suppose this is my center line. So the center line got shifted something like this. So we will have a distance. This is we call delta. Okay, this we call delta. In you can say shorter lengths, it is very rare to see this kind of behavior. But whenever the column length is higher, in such cases, this flexural buckling we may see, and due to this behavior, again you can see the center line of the column is shifted, and here we are having PU. So due to this P multiplied by delta, that means this shift, we will be having some additional moment. We will be having some additional moment that we need to consider for our design. Okay, so along with this M1, M2, M22, both directions, we will be having some additional moment. Now additional moment can be of another type. Suppose we have a frame. Suppose this is my beam. And my columns. Okay. Fine. So now what is happening? We have, this is my center line of the column. Okay, so we are having the axial loads on this also, and suppose we have some lateral force on it. So it is the lateral load or lateral force, I will say. Okay, so due to the lateral force, what will happen? We will be having the sway of the column. So it will be something like this, we will say, if we consider this as fixed. Okay, this kind of behavior we will get. Now here also, if you see, the center line of the column got shifted, and again obviously this load will be there, this load will be there, right? So due to this distance, this shift, we denote this shift as big delta. So again, obviously, due to the lateral load, there is due to the sway of this frame, okay, we got this delta, which is the displacement, right? And then again we have pu on it. Okay, we have pu on it, that means the axial load. So due to this, again, due to the effect of pu multiplied by this shift, we will be getting some additional moment. Right? So these additional moments are more effective, or more, you can say, applicable when the column lengths, or the unsupported length or effective length of the column is higher. Then there is a chance of getting higher value of this additional moments. Fine. So now code has a criteria regarding this unsupported length, that which we call the slenderness ratio. So the slenderness ratio if you see in here only, yes, here, if you see 25.1 column short and slender compression members. So a compression member, that is a column we are considering, may be considered as short when both slenderness ratios Lex by D and Ley by B are less than 12. Okay, it shall otherwise be considered as slender compression member. So when we will be considering the column as short column, when suppose, again I am drawing the section, this is my axis 1 1 and 2 2, and this is D and this is B, and we have L effective. Now it is talking about L effective. Now what is this L effective? So if you see, suppose, let me draw here the beams, okay, and the column. Fine. Now this zone, if you see this particular zone, this zone is very rigid zone, and these joints are not simply supported, not fixed. These joints we call as rigid joints. So these are my rigid joints. So when the column is going to buckle, so it will not buckle from the center of it. It will not buckle from like this. Okay, it will not buckle like this. Again, it will not buckle from exactly from the bottom of the beam also. No, it will not buckle like this. So how it is going to happen? So the exact behavior of flexural buckling, if you see, sorry, so it will be having something like this. Though it is not exactly the correct one, but still, just for your understanding. So the buckling, so this is my unsupported length, L unsupported. Okay, but the effective length, if you see, the buckling started happening from here, for this from here. So this distance from where the actual buckling started happening, so we call it as L effective. Okay, so how to find this L effective? Now the code has given us a process to find the L effective, which is K multiplied by L unsupported. which is my L effective. Okay, now how to find this K? This is a factor which will give you, like, which will help you to find this particular you can say area. Now how to find this K? To find the L you can say effective. So for that, if you go to our code, let me go to NXE. Yes, NXE of our code, and here you can see there are two methods. One is using this table number 22, which is not applicable in all like you can see here, different conditions of column connection. Okay, here we have flexural buckling, we have sway effects. But the thing is, if you see this particular table, we do not have any such condition. We do not have a fixed condition, both end fixed. We do not have both one end pinned, one end fixed. We do not have both end pinned. We do not have this condition also, this condition also. Exactly this kind of conditions you cannot get, because our joints are not fixed, not either, not it is not fixed, not pinned, not any other you can say common connections that we are seeing. So this is the rigid connection, right? That means the angle between these two members will be always 90 degree, and then it will give you the deflected shapes, right? So for the rigid connections, what we have our code has given us is this process. So this is explained in NXE. So first of all, to understand to find out the K, which is the ratio of L effective by L unsupported. Okay, so for this, what we have to do, we have to find this Q value, which is the stability index. Okay, so this stability index you need to find out using this formula, which is PU, summation of PU. So what is this summation of PU? Suppose this is my frame and this got shifted like this. So we have this PU here, we have this PU here. So for a single frame, suppose we need to add both these PUs, PU1 and PU2, and then you will be getting this PU. Okay, then we have delta U. So it says that the displacement due to the ultimate loads, okay, whatever displacement we got due to the ultimate loads, we need to add. Then HU is nothing but the lateral force due to the ultimate load, ultimate combination you can say, or ultimate load you can say, total lateral force acting within the story, total lateral force in this particular story. Okay, and HS nothing but the height of the story, this height HS. Okay, using this you can find out this Q factor. Okay, now how to do this, I'll be telling you the fact in a while, just wait for it. So we got this. Now if the Q value that we have got, if it is less than or equal to 0.04, then the column in the frame may be taken as non-sway. There will be no sway in the column. And if it is greater than 0.04, then we'll be considering the frame or the columns that we are designing as sway column. Now for sway and non-sway column, there are two charts given in our code. One is, you can see this chart for no sway, and this chart for sway column against sway. Now if you see, to find out this effective length factor or effective length ratio, L effective by L, which is my K, for this we need to have two variables, which is beta 1 and beta 2. And how we gonna find out this beta 1 and beta 2? To find out this beta 1 and beta 2, here is the formula given or the process given. One second. So it says beta 1 and beta 2 are equal to summation of Kc by summation of Kc plus summation of Kb. Now let me explain this. What is this thing? So if I go to jump into my whiteboard again, okay, and let us write it here that this is my C Suppose this is my C1, this is my C2, this is my B1, this is my B2. Okay, and let me draw another beam here for your understanding. Okay, so this is suppose B3. Okay, now if I am talking about this area here, we have two joints. So this is my beta 1, this is my beta 2. Okay, so how we will be finding beta 1? Beta 1 will be stiffness of bottom column plus stiffness of top column. Okay, that's why it says summation of Kc. Okay, so that means Kc1 plus Kc2. This is what we are getting, right? Let me check. Yeah. Kc2, stiffness of C1 plus stiffness of C2 divided by Kc1 plus Kc2. Sorry, I have written wrong. Kc2 plus summation of stiffness of these beams adjoining in this particular joint. So here Kb2 plus this stiffness of Kb3. So Kb3. This will give you beta 1. Similarly, you need to find out for beta 2. Now it is very easy because we do not have any top column. So it will be beta 2 will be Kc2 divided by Kc2 plus Kb1. After finding this beta 1 and beta 2 from this formula, you need to find out the effective length vectors from here. Okay, now you will say that how we gonna calculate this? See, for a simple frame you may calculate the stiffness of the columns and beams, but for a you can say three-dimensional frame, for a complex structures, it is hardly possible for anyone to calculate this manually. Okay, it is hardly possible for anyone to calculate this manually. So in that cases, we used to take help of our software programs, the trusted software programs like ETAP, StatPro and all. But again, there is a issue in the StatPro that I will be telling you. Now, for no sway frames, it is okay for you. You can take one conservative approach. So if you see beta 1 and beta 2, considering this, the maximum value that we are getting for K is 1. So that means in that case, L effective equal to 1 into L unsupported. So we can consider the L unsupported length as our L effective length. Okay, that is fine. Like that will be a conservative approach in case of no sway frames. But in case of sway frames, if you see, in case of sway frames, the value of K can be infinite. Okay, so what is the meaning of infinite value of K? That means whenever your K factor is higher, obviously you will be having higher amount of displacements or higher amount of, you can say, lateral displacement. Okay, and if it is infinite, that means your frame is it's not stable. Okay, so you will find instability errors in the softwares. It will give you instability errors in you can say StatPro or ETAPS. Okay, so that means your structure is not at all standing. It has no resistance towards this particular you can say lateral force. So finding for the no sway frame, it is okay. You can take any value which is 1 as a conservative approach. But what about this particular thing? What about the sway frames? Some people say that we used to consider 1.2. Some people say we used to consider highest value as 2. Like if you see this particular thing in table number 22, so there are some you can say concepts given by some practicing engineers that we consider 1.2 for this. Okay, some will say that we will consider 1.5 for this. Some will say we will consider 2 for this, because these are the conditions, this kind of conditions we may get. right? We also can take 2 from this also. Now the problem is that in our chart, if you see for the no sway frames, the value of k can be more than 2 also. The value of k can be 2.5 also, can be 3 also, can be 4 also. Obviously these values are not desirable, but it can be 2.5, right? It can be more than 2.5 also. So how do you decide this? So obviously in that cases, manual calculation or considering the values from the table number 22, it's not a right approach. So our software program, which is eTabs, it is capable of finding out these values beta 1 and beta 2 based on the stiffness of the beam and column. But StatPro, this is the lacking of StatPro. StatPro is not capable of considering the the K factor automatically. So it cannot calculate the K factor based on the stiffness formula that is given as of now. Okay, so for steel frames, for steel structures, we have different measures. We do not consider the steel frames as moment frames. We use the bracings and all, and we use the formula value from the no sway chart. For steel also you will have this kind of chart there actually in IS 800. So we consider 1 as the maximum one. But for concrete, you cannot use, you do not have any other way of transferring the load rather having a moment frame. Okay, so in that case, how we'll be doing this? So obviously we have to take, either we have to calculate it manually, the stiffness, and we find out the beta 1 and beta 2 and have the exact value of K, or you have to rely on the software programs like SAP 2000 or eTabs. Okay, or any other software if they are capable of. But StatPro as of now is not capable of calculating this K value as of now. So you'll see that in StatPro there is EL, I think ELX and ELZ, something like this is given. Effective length factor about x-axis, effective length factor about z-axis that you need to input. Okay, so this is very, because it is a harsh reality that you cannot put these values for the sway frame properly. Okay, now in general practice, as I said, some people used to take 1.2, some used to take 2. So that is general practice. But how you can decide whether it is 2 only? It can be more than 2 also, right? It can be more than 2 also. So that is the issue with our StatPro software. Fine. So now as we got the K value, then we can easily find out the effective length. So we got the effective length here. Suppose, let me go to my whiteboard. So we got the effective length. Now we'll be finding out the slenderness ratio. So slenderness ratio we need to find out for both axes. Suppose, see, if I am finding out about 1 on axis, so it will be for 1 on axis, it will be L effective by D, and for 2 to axis it will be L effective by B. Okay, now if it is greater than 12, then suppose one axis is greater than 12, other axis is less than let me draw it something like this, that here suppose it is less than 12 and this is greater than 12. Then also we'll be considering this column as slender column. If both axes are less than 12, then only we can consider it as short column. Okay, so whenever the effective length by depth or width ratio, that means the lateral dimension ratio, is greater than 12, then we need to divide it, we need to consider the column as slender column. Now what else after considering this as slender column? So now if you go to code again, IS 456, in page number most probably 71, yes, I have written it actually for reference. So page number 71, you will find this option, or you'll find this method. Yes, here. So it is the additional moment. What it says that the design of slender compression member shall be based on the forces and moments determined from the analysis of the structure, including the effect of deflections on moments and forces. When the effect of deflections are not taken into account in the analysis, additional moment given in 39.7.1 shall be taken into account in an appropriate direction. Okay, so what is this moments determined from the analysis of the structure? What does it mean? That if you are doing the P delta analysis, so it is a very complex method. Okay, maybe some of you say that I can do it in software, but you can do it in software, but do you really understand how it is doing? Okay, if you understand, then it's fine. If you understand the behavior, if you think that behavior is correct, then it is okay. But if you not, then what it says that if you are not considering the P delta effect in the software itself or any analysis itself, then in that case some additional moment need to be added in your column design. So this additional moment, so I think this is the I can say safe approach for us, unless going for a blindly software approach. Okay, so here what it says that we can add some additional moment. So it can be PU by D or B. Actually it will be M additional equal to PU by into D or B, whatever is the lateral dimension, divided by 2000 multiplied by lambda square. Now what is this lambda? Lambda is nothing but my slenderness ratio. So lambda equal to L effective by D or B. Okay, L effective by D or B. So you can find out the additional moment for both the axes. Now again, with this additional moment, you can do some, I can say, you can play with this actually. So if you see here in 39.7.1.1, the values given in the equation 39.7.1, that means this one, the additional moments, may be multiplied by the following factor. So now this moments, additional moments that we are getting, it can be also reduced using this particular factor when it is a compression member. Okay, when it is a compression member, and you can also read these things actually. The criteria is given here. Okay, so if you these criteria are matching with your condition, then you may you can say do the reduction of the additional moment using this K. So how you need to be reduced it? By using this PUZ minus PU by PUZ minus PB, it should be less than or equal to 1. In most of the cases, the highest value, that means it will be 1. You can consider it as 1. So if it is 1, that means there is no reduction. If you want to reduce it, then you need to see this PUZ, how to find out this PUZ. So here it is the PUZ. 0.45 FCK into AC, that means area of concrete, plus 0.75 FY into ASC. AS means steel under compression. That means the steel you are going to provide in column. Now we'll say that how you'll be finding the steel before doing the design. All of you know that in column design, we do not find the steel. We check the provided steel. Okay, we check what is the interaction. We need to check what is the capacity we are getting after providing that amount of steel. If the capacity is more than my analysis moments or analysis forces, then it is okay. If it is less, then we need to redesign. Okay, so this ASC, that is the area of steel in compression, actually you need to consider. Suppose we will begin with 1.2%, 1.4%. Okay, you may begin with 0.8% also. Okay, I need to check what is the 0.8% means 0.8% reinforcement, minimum reinforcement. This is, then you need to check the interaction. So that's why column design is a bit complex than the beam design. You are not finding the reinforcement, but you are checking the reinforcement by deciding one particular percentage. In software, it does actually this iteration again and again. It will start with 0.8, 0.1, like 1.0, 1.2 like this, and wherever it is meeting the I can say criteria, it will give you that reinforcement. Okay, so now What is this PB? How you'll be finding out this PB here? This PU is nothing but the axial load you are getting in the column. And what is this PB? PB is nothing but that you need to get from SP16 actually. If you see our SP16, page number 171 and table number 60. So slender compression members, value of PB. So here it is a formula, PB by FCK multiplied by B into D. That means the dimension equal to K1 plus K2 into P by FCK. This P is nothing but the percentage of reinforcement, PT. Okay. So here it is given the K1 and K2 value, or you can say different. The K1 value is based on the D dash by D. Okay. What is D dash by D? I think in the beam design also we have considered this actually. D dash is nothing but what is this D dash by D? I think we have calculated. Okay, that I will explain later. Okay, because we'll be doing this D dash by D in a while. So I will explain this later. Okay, so we need to find out this D dash by D. Okay, that means effective depth for the compression bars. So that we will see D dash by D, and we need to check whether your column is rectangular or circular. So you'll get K1, and then we have K2. So now for K2, there is some limitations. If you see, it says the rectangular section equal reinforcement on two opposite sides. So there are different conditions given in code. So it says equal reinforcement on two opposite sides. When it is about this axis, it is not given for this particular criteria. When you are finding out for this axis and it is like this, it is not given for this actually. We do not have any such condition in our code. Okay, so this is one criteria, and again another one is equal reinforcement on all four sides. So suppose this is my axis, we are finding out for this axis, so it will be 1 2 3 1 2 3 1 2 3 1 2 3. Suppose 3 reinforcement from all the sides we have. In that case, we will be using this. Based on the grade of steel and based on the D dash by D ratio, you will be finding out the K2 value. Then you put it here in the formula. The formula for rectangular and circular section. Then you find out the PB from here. Okay, after finding out the PB, you can put it here in the code and you find out the K value. Okay, so if the K value, once you get the K value, you can multiply this K value with the additional moment, and then this additional moment you will be using for the design. Fine, I hope it is clear. So the slenderness effect we considered, and due to the slenderness effect we found out the additional moments also. Okay, now what we will be doing? So we got, what are the things we got? So it was the analysis forces. So we got PU, M11, M22. Among this we have ME1, ME2, whichever is higher we will be considering this, plus we will be having additional moment. So MA11, MA22 if the member is slender. If not, then we will not consider this. If slender. Okay, so we got the forces here. Now we will go for the design. So how to design it? So first of all, you need to decide some percentage of reinforcement for the section. Okay, first of all, you need to decide some percentage of reinforcement for the section. If you see, suppose like this, you are providing. Okay, suppose you have provided like this, and suppose these bars are, how many bars we have provided? 1 2 3 4 5 6 7 8 bars. So 8 bars of T16 suppose, and this is suppose 300 by 300. And what is the scenario? It is four side equally distributed. Okay, So what is the reinforcement percentage we can find? So 8 bars of 16 means 8 into 200, 1600 mm square. Okay, so what is the percentage of reinforcement? 1600 mm square divided by 300 into 300. What is the percentage of reinforcement we are getting? Please tell me. Calculate this and tell me what is the percentage of reinforcement we are getting. Are you guys? 1.11. So 1.11 percentage we got. So this is, we assume that we are providing like this. Okay. So most importantly, percentage of reinforcement obviously you need to consider, but most importantly, what is the distribution you are going to provide, that you need to check one if you are doing manually, because depending on this distribution only we'll be finding out the interaction curves. Okay, so there are different you can say things that I'll be telling you. So in our code, that is SP16, in our handbook, we have only two cases. I'm not talking about the circular one. Obviously circular one is there. So if I talk about the rectangular or square case, so we have only two cases. Okay, so suppose this is my major axis. So suppose I am finding the capacity about this axis. Okay, so this is my suppose 1 axis. I'm just writing it here. Okay, so in that case we have one you can say aspect, which is the reinforcement is distributed equally in two sides. That means two sides of your major axis, or two sides of the axis for which you are finding out the capacity, or equally distributed in all four sides. For rectangular or square case, okay, we have only these two. But if the case is something like this, that we are finding the capacity about this axis and it is equally distributed like this, like the previous one. So now the reinforcements are not in the opposite sides of the axis, but it is perpendicular to the axis, this reinforcement distribution. Or if you say like this, suppose I am finding for this axis only, but reinforcement distribution is given like this. Here also it is perpendicular. For such cases, we do not have any interaction diagram in our SP16 code. Okay, or in the SP16, it's not code, it is the handbook. So we do not have any interaction. But luckily, our softwares like eTabs, RCDC, StatPro is not capable. Again, StatPro is not capable of doing it. StatPro has these concepts only, whichever is given in code. Okay, so eTabs, RCDC, they are capable of finding out the, you can say, capacity or interaction diagram for any kind of distribution, for any kind of column shape. Okay, these softwares are capable of finding out the interaction diagram. Okay, so these are the limitations of StatPro with, if you compare with the eTabs. So once you have RCDC with StatPro, then it is okay. Then again, you can do it actually in RCDC. Okay, so now once you get the distribution for this, so what you have to find out? You have to find out the d dash by d. So why we need to find out the d dash by d? Let me go to my SP16 code to tell you. Actually, we need to find out the interaction diagram. So what is this interaction diagram? Let me tell you first this. So suppose now which are the things that will be interacting? One is PU, M11, M22. These three things will be interacting with each other. I have considering that this M1 and M22, including the additional moment or the eccentricity moment and all. Okay, including all this, you'll be getting the final moments and the lateral, the axial load. So now, how the interaction diagram will be? It will be my suppose PU. This is my suppose M11. Okay, PU by M11. So you have got some value of PU. You have got some value of M11. Okay, so what code has given? The code has given, or the handbook has given some capacity curve like this. Even you can also find out the capacity curve like this. So what is this? It is the maximum axial load carrying capacity. It is the maximum. Suppose I will write it like this actually. I will not first give this. So it is the maximum load carrying capacity, axial load carrying capacity, and maximum moment carrying capacity about one particular axis. Okay. So in that case, I can write like this. Now, whatever load you are getting, suppose these are your analysis forces. So due to the analysis forces, if the interaction is coming, if the interaction point is coming, or the diagram is coming like this, or if you draw the interaction curve, if it is falling inside this particular curve, the capacity curve. So this is the capacity curve taking the maximum values. So if you are having the point like this, then it is passing. If your capacity due to the analysis forces, if the curve is going like this outside of your capacity curve, then your column is failing about that particular axis. Similarly, so now you take like this, PU, M11, M22. So the capacity curve about this axis, the capacity curve about this axis. So it is the two-dimensional representation as per our code. You will get two-dimensional representation. But actually the column is a three-dimensional member, right? Okay, so in that case, you need to have a three-dimensional interaction diagram or interaction curve. So it will be like this. So actually you are getting a three-dimensional interaction surface like this. So it is the interaction surface. So now if your point, due to the axial load analysis moment, if your interaction point is inside this particular surface, then it is passing, or if it is outside the interaction surface, then the column is failing. Okay, now it is not possible for us to find out it manually, this three-dimensional diagram. So that's why what we do, we deploy this three-dimensional diagram into two-dimensional diagrams that I have just explained. One for PU M22, one is for PU M11, and then we consider the you can say we check the two capacities, or you can say two things interacting, how it is interacting with each other. Okay, so that I will tell you one just now. So if I go to my code, and if you see here, I think, yeah, here you can see compression with bending, rectangular section, reinforcement distributed equally on two sides. This is one particular case. Now for this you need to have the Fy value and you need to have d dash by d value. Okay, you need to have d dash by d value. Now what is this d dash? D dash is nothing but the, as I said, effective cover to the compression reinforcement. So obviously for the column, all the reinforcements are compression reinforcement, right? So you can consider this as your effective cover, and d is nothing but your total dimension, total depth. Okay, so that will never change, I guess. D dash by d, yeah, it will change depending on the dimension actually. Let me check how it is. Yeah. So now how we'll be finding out the d dash by d? So it will be the effective cover by my dimension. So if you are finding out about this axis, this here will be your d. If you are finding out about this axis, then it will be your d and it will be your b. Okay, here do not get confused about this d. D means if you are finding out about this axis, then the perpendicular face will be your d here. Okay, so you can just remember it b or d like this. So d dash by d, if you are finding about the axis which is perpendicular to this dimension, or b if it is perpendicular to this b dimension. Fine. So you got this d dash by d. You got the you can say Fy value, which is the yield strength of your steel bars. Okay. Now what you have to do? Just give me 1 second. Okay. So now what you have to do? You have to use this. You have to find these formulas, or you have to find these values. One is Pu by FCK BD and one is PT by FCK. Okay, these two things you need to find. Okay, so how are you gonna find this? Let me go to my. So what are the things we need? First, we need the Fy value. Okay, we need by the d dash by d. So from these two, you can choose the curve that you will be using, which curve you need to use, and also the reinforcement distribution. Reinforcement distribution. Taking these three things in mind, you will be finding out the curve from SP16. Okay, so there are one curve for, as I said, reinforcement in opposite directions, and another we have for all four sides. You can see equally distributed in all four sides, and obviously for the circular columns also we have. Okay, fine. So now what you have to do, once you get the d dash by d, you have the Fy, you have the reinforcement distribution, you have chosen the curve from here. Suppose you chosen this curve. Now you need to find out Pu by FCK BD square. So what is this Pu? My axial load. FCK is the compressive strength of concrete. B is my width of the section. D is my depth of the section square. Again, I am saying if this is your section, if you're finding about this axis, then this will be your D, this will be your B. If you are finding about this axis, this dimension will become your B, this dimension will become your D. Okay, so rather changing these dimensions, you can keep this in mind. Then one it will be BD square, another will be DB square. That also, like whichever process is you can say easy for you, you can keep it in, you can remember it in this way. Okay, so you got Pu by FCK BD square. Another one you need PT by FCK. Right? PT by FCK BDS, I guess. Okay, PT by FCK. Fine. So you got these two values. Obviously, it is very easy. PT, we have already considered 1% of reinforcement. Using this both axes, for M11 axis once, for M22 axis once. For both axes, you need to find this. You got this two. Now you will be finding out the mu by FCK BD square from the chart. So if you see here, mu by FCK BD square, how will be finding out? You got, suppose, the Pu by FCK BD somewhere here. You got the percentage of reinforcement, though maybe I am going very higher, it will not be like this. Suppose here, so you will be choosing like this, and you will be choosing like this. So you got somewhere here, it is between 0.1 to 0.2. So maybe you can say 1, 2, 3, 4, 5. Okay, so it is 0.05. It is 1. It will be 1.05 or maybe 1.06 will be your mu by FCK BD square. So something like this you need to find. So once you get mu by FCK BD square, so what you will do? It will be something like this. It will be mu11 FCK BD square equal to something, suppose 1.06. Now you can find out the mu11. So this will be my capacity. So you can write, even you can write it as MC11. Okay, so MC11 equal to 1.06 multiplied by FCK multiplied by B into D square. Similarly for this one, MC22 will be whatever value you got, suppose 1.02 multiplied by FCK multiplied by BD square, and again if you want you can change it to DB square also, means if you are not changing this way. So you got the moment capacity. Now if these moment capacities are greater than your moment values, analysis moment values, then you are safe. If not, then you have to increase the percentage of reinforcement, you have to increase the size maybe, or you have to check the reinforcement distribution. Okay, so now we have checked for individual axes M1 and M22. Okay, now what about when all these three will be interacting with each other, right? So in that case we need to use this method, given here. Okay, so MUX, that means the analysis moment about x-axis or whatever axis it is, divided by capacity of this axis, that just now we found out. Similarly, plus MUY by MUY1, and then we have this alpha n. If it is less than or equal to 1, then it is safe. If it is greater than 1, then it is unsafe. So this is called my interaction ratio. Okay, this is called my interaction ratio, or you can say utilization ratio. Okay, so now how to find out this alpha? For this also everything is given actually in code. If you see here, this alpha value is depending on the PU by PUZ. So PU you already know what is the axial load. Now what is this PUZ? PUZ is this formula which I have explained earlier. We've said if PU by PUZ is 0.2 to 0.8, if the value of PU by PUZ actually varies from 0.2 to 0.8. Okay, so now the values of alpha n varies from 1 to 2. Okay, now when will be 1, when it will be 2. So for values less than 0.2, that means for PU by PUZ value less than 0.2, we'll be considering alpha n as 1. For values greater than 0.8, we'll be considering 2. If there is any value which is in between, then you can do the interpolation. Like for PU by PUZ 0.2, alpha n is equal to 1. PU by PUZ 0.8, alpha n is equal to you can say 0.8. So what is the you can say intermediate value? We can easily find out. Okay, so once you find out, you got the PU by PUZ, you got the alpha, you just put it this in formula. So my analysis moment by moment capacity alpha plus analysis moment by moment capacity alpha. You got the interaction. If it is less than 1, it is okay. If it is greater than 1, this column is failing. That means the column is not passing with that particular capacity. Okay, now if this interaction ratio is 0.3, 0.4, 0.5, what you understood? That you have used over, you can say the capacity is over. Okay, that means it is not a you can say, I would say it is not a optimum solution or optimum section, or maybe you have provided a higher amount of reinforcement. Okay, so in that case you may reduce the reinforcement, you may reduce the column sizes and check. So we used to try to keep it in 0.7, 0.8 or 0.9 in such cases. Okay, so that means it is a optimum solution you are getting. Okay, so this is how you can design a column for, see, it is it is given here, biaxially loaded column. Member subjected to combined axial load and biaxial bending. Okay, so this is how you can design the column manually. I hope the whole process is clear to all of you. Any questions? Let me check. Let me check on YouTube also. Yes. Yes. Just give me. So I will write it here itself. First, we will find out analysis forces. Okay. Then second, minimum eccentricity. We will compare with the analysis moment. Whichever is higher. Okay, so this is not the second, actually this is a additional one. Third, we will be having slenderness ratio and slenderness, let me write it like this, moment due to slenderness. Moment due to slenderness. Okay, then we will add this. We got the final results. Then what we will do, we will find out the interaction diagram using this. First we will choose the diagram from d dash by d, and another one is Fy and reinforcement distribution. Using these three, we'll be finding out the chart from SP16. And then we need to find out Pu by FCK BD square, and we need to find out PT by FCK. Using these two, we'll be finding out the Mu by FCK BD square. From here, we will be finding out this Mu, that means the moment capacity for each direction. Once you get for each direction, if it is less than the moment capacity, it is fine for the each particular direction. Now we'll be doing the interaction. So Mu by MC, suppose Mu1 by MC1 alpha plus Mu2 by MC2 alpha. If it is less than or equal to 1, okay. If it is greater than 1, not okay. Clear? So actually now it is hardly possible to go through all the things. So this is the brief of whatever we have done today. Okay, so this video will be obviously available in YouTube also. You can watch it later also if you have doubt. Okay, so let's see, let's have a quick view what software does in this particular case. So as I said, whenever you are performing the design preference, this design preference and the design overrides are very important. So you can see here, design code IS456, number of interaction curves, like it is for the 3-dimensional interaction curves. So you can, as more as possible you can provide, but as by default I have chosen 24 itself. Number of interaction points, let's leave it. Now consider minimum eccentricity, yes or no? Do you want to consider minimum eccentricity? Obviously we want to consider the minimum eccentricity. Consider additional moment. We have not performed P delta analysis, so you want to use additional moment in case we have slenderness effect. Consider P delta, see we have kept it no. Design of BC ratio, so these things actually, are not as per IS456. This beam column capacity ratio is as per IS13920. That's a different topic. Ignore beneficial PU for beam design. Now these things are of beam design. So you can see these three things are of my column design part, right? Now again, if I go to my overrides, so if I you just have to click on these columns, and if you go to design concrete overrides, This is my column size. And now again we have the framing type, ductile, ordinary or non-sway. If you consider ductile, the software will consider the frame as ductile, means it will calculate Q, stability index. From there it will find whether it is sway or non-sway, and it will design the frame or design the members as per IS 13920. If you consider sway, see here we have sway, sorry, ordinary. If you consider ordinary, what will happen? It will design as per IS 456, but it will consider the K value from the sway chart. If you consider non-sway, it will design the section as per IS 456 and it will consider the K value from no sway chart. Fine. So for now we have considered no sway only, and I have clicked on 1. So now again one more thing, you see effective length factor. See, it has calculated based on the beam and column that we have provided. Based on its stiffness, it is considered 1.266. Some people, you will see, this is about one axis, about another axis. One is unbraced, effective length ratio for sway, and braced. Obviously our columns will not be braced here. Okay, so we will check this too, sway. Okay, now some people will say that it is giving higher value, 2.5, 3.5. It is not correct. You will see some people are saying like this, that the effective length ratio given in calculated by ETABS, it is coming more than 2.5. It is coming 2, more than 2. But it can come 2, right? Because in the chart that we have seen in the code, we have values up to infinity. So 2, 2.5, 3, it can come based on your how you have distributed the forces, lateral forces through your frame. Okay, how it is displacing, what are the, you can say, lateral resistance you have. So based on that, whatever sway it is coming, sway value we are getting, based on that it will be calculating the K. So there is nothing wrong doing done by the software. It is you that you have chosen which type of frame or what type of, I can say, arrangement. Okay, so don't get confused while having the values very higher. If it is very high, like 5, 4, then that means your structure is unstable. It is not stable, so you have to check your framing system or maybe whatever force resisting system you have chosen. Fine. Now I'll click on OK. And now if I click on design, it is already designed actually. Now take any column, right click. You can see it has designed in 3 locations. One is at the top, at the bottom, at the middle, at the top. Okay, so we'll take any of this. You can see the interaction diagram by clicking this interaction diagram. You can see this is the interaction diagram. PU, M2, M3. Okay, so in this column, M2 is almost 0. So now you can say this is a uniaxially like axial load with uniaxial bending. Okay, so only one direction we have bending. So this is the interaction curve that we have got, interaction surface that we have got. It is a 3-dimensional surface, right? Because our column is also 3-dimensional. So for every single point in the column, it has generated the interaction surface like this. Okay. Now if you see the details, now this is what it is important for us. I'll go to flexural details. Shear design, it is same as beam and all. So I'm not going to consider show you this today. So the important thing is this one. So as we have seen in the beam design part, the column numbers, column size, the critical load combination, station location, at which location it is designing, total length of the column. Okay. Then clear cover, it is considering here as per our input, the design, 500 and 415 FY, and for main rebar and for stirrup, grade of concrete. Now here is the thing that we need to see. So let me see whether it is given at the bottom also. See here, additional moment reduction factor K. Do you remember which one is this? Additional moment reduction factor. Do you remember which one is this? So K is equal to PUZ minus PU divided by PUZ minus PB. Remember, we have found out the PB from SP16. It should be less than or equal to 1. So here you can see PB it has got, PUZ it has got, PU it has got. Okay, and area of compression steel also it has got. Gross area also it has got. Using this from that particular chart, we can find out the K value. So here we are getting the K value, which is 1. Fine. So that means there will be no reduction in the additional moment. Now you can see the additional moment. Additional moment. What is this additional moment? Can anyone tell me? M additional moment is equal to PU by how much it was? PU into D by 2000 multiplied by lambda square. Okay, so first we got the slenderness ratio, L effective by D or B for both directions, and as my column size is 300 by 300, so we got the similar value. Now it is less than 12, so there is no way of adding the additional moment. There will be no additional moment, so that's why there is no additional moment. You got it? There is no additional moment. Now we will go down. I think okay, flexural design. We changed to shear design. Why? Let me show you here itself. Yeah. So these are the analysis forces PU, MU2, MU3. Okay. Now what is this? What is this? Can anyone tell me what are these values? Minimum M2, minimum M3. How we have got this? So these we have got from the minimum eccentricity, PU multiplied by E for both directions. Now among these, the analysis moment and the moment due to eccentricity, we are seeing that the analysis moments are higher. So we'll be using these two as my design moment, like for the design, not these two. Okay, got it? Then if you go down, let me show you here. This is not important now. Let me see from here. Slenderness effects. As I explained, minimum biaxial moments. I should start from the bottom actually, so that you can understand this. Yeah, additional moment if you see here. As we got the slenderness ratio less than 12, so there is no additional moment. Right? Additional moment factor K, so 0 into 1, so it will be 0, there will be no addition. Now here if you see effective length ratio, actually software calculates the both for sway and non-sway, but which one it considers? As we have considered the framing type as non-sway, so it is considering the K value as non-sway itself. Now you can see it has not calculated the Q factor. Why it has not calculated the Q factor? Because the Q factor will be only calculated when we are considering the frame as ductile frame. Okay. In other cases, in ordinary case, it will directly take the K value from the sway chart, and for the non-sway case, obviously it will be considering from the non-sway chart. So we've got 0.595329, and this is for the sway. If you have sway case, then it will be this one. Okay, so for now the effective length ratio is considered as 5.5935229. Fine. Then we go up this, so this initial moments, it is not required for now. These are the end moments. That means it is considering moment at this position, moment at this position of the beam column. Okay, like this it is having the end moments. So minimum eccentricity moment we do not require because our moments at the end are higher. Okay, minimum eccentricity E value we have got here, it is 20. So there is a criteria that whatever minimum eccentricity we are getting, if it is less than 20, then we will be considering 20 as our minimum eccentricity value. Okay, so that means E value, if it is less than 20, then we'll consider 20 as our minimum eccentricity. Okay, if it is greater than, then we'll be considering the greater value. Okay, so now why this Ka is into K into Ma is 0? Because our M value, additional moment, is 0, K is 1, so we got this value as 0. Fine. Now if I go up, see, no sway is considered. Okay, the factored moments, and for this now we have got the reinforcement area. So the software starts with 0.8%, and it's after checking the interaction diagram, means after checking the interaction for both axes, it is found out that this 0.8% reinforcement is okay for our section. So this is the reinforcement area that we are getting, which is 720 mm square. Now you need to distribute this 720 mm square. Now the most important thing is how you gonna distribute. At the very beginning I have given the definition of this: equally distributed in all four sides. Okay, so if you want to check the interaction diagram and the reinforcement along taking this reinforcement percentage, if it is passing or not, if you want to check manually with the software result, then you have to provide whatever we are it is available with us. But it is not compulsory for ETABS or SAP 2000 that you have to provide like this only, because these softwares are capable of you can say finding out the interaction diagram for any kind of distribution. Okay, so I hope this design result given by ETABS, how it is doing, it is you can say clear to all of you. Okay, now if I go to StatPro, the same thing. If I run the analysis, and here one thing you see, I have given one command which is this rface. So you can see this in rface command we have these three cases: phase distribution about major axis, phase distribution about minor axis, longitudinal reinforcement in column along four faces. Okay, so I have chosen this longitudinal reinforcement in column along four faces. Okay, whichever I have chosen in the ETABS case. Now if I see the analysis output, and I'll directly go to column design. So you can see the grade of steel, grade of concrete, length of the column, cross section size, cover we have considered. So design axial force, this is the axial load, 54.30 kilonewton. Okay, initial moment, that means the analysis moment, 14.43 for both axes. Moment due to minimum eccentricity, 1.09. So which will be considered, these values will be considered. Slenderness ratio dash dash, that means there is no slenderness effect. Moment due to slenderness effect, obviously there is no slenderness, so no moment due to slenderness. Moment reduction factor, the K value, which will be multiplying with this moment slenderness due to moment, so it is also 0. Additional moment, obviously as these things are not available, so there will be no additional moment. So total design moment is 14.43, 14.43. Okay, now how it has found out the required steel area? So it has applied some reinforcement, percentage of reinforcement, and using this PU MUZ1 and MUY1. Okay, after applying this reinforcement percentage, it has found out the capacity ratio. So if you see the capacity ratio, it has given or not? Section capacity based on reinforcement. Yeah, interaction ratio, if you see, it is 0.98. It is given interaction ratio as 0.98. That means very optimum design it has done. But now there is a problem in StatPro. This is one more problem, that here you can see the percentage of reinforcement assigned, it is 0.5%. But as per our code, the reinforcement, at least 0.8% reinforcement should be applied in our column. This is the minimum reinforcement criteria. So this is the problem with STAT, that STAT applies less than 0.8% also in case of column. Okay, so you cannot rely on these results. You have to check again manually. Right? Now, as our reinforcement distribution is all four sides, so obviously you can easily check from the you can say SP16 curves. You can directly take the PU and analysis moments from here, and by putting those there in the curve, PU by FCK BD square and PT by FCK, you can find out the moment capacity. Okay, so this is how the STAT does, but these are the flaws that STAT are having actually. STAT have these particular flaws, that it provides less than 0.8%, and also we have these you can say limitations in terms of the reinforcement distribution. Again, as I told you, the effective length factor is not calculated. So as the effective length factor is not calculated, as I am considering this as non-sway frame, so I am considering 1 as the maximum value. By default it will take 1. But if it is a sway frame, then you have to put this command, which is, you can see ELZ and ELY, where it is, yeah, ELY, ELZ. So now this ELZ and ELY, what value you will put, whether it is 2, 2.5, 3, 1.2, what value you will put. Okay, so that is the limitation of StatPro. Either you have to calculate manually and you have to put it here, or you have to go for so like blindly some value and you can go for it. Okay, so I hope these things are very clear to all of you. Any doubt? So we'll be taking the doubts now. Let me take, actually I'm not connected to, I'm not seeing the comments on the YouTube also. Let me check once if there is anything on the YouTube. And if you have guys also any question, you can tell me. Any questions? Okay, let me check in the chat box. FST I didn't get actually. Rahul, what use of FST demarcation in charts? I already explained, right? Please explain how to perform P delta analysis with all load cases in ETABS or correct calculations. No, see, if you see, P delta analysis is not required for buildings less than 50 meters, like if it is not tall building. Okay, because there is nowhere it is mentioned in the code. So there is no way, like no requirement of going for the P delta analysis, right? You can directly consider the additional moment and you can design. If you want to do that P delta analysis, then there was a draft, you can say edition of IS 16700, which is not available now, I don't know, for some reason, where they have given the load combinations that you need to consider for P delta analysis. Okay, but I have not found in any other places actually how to do that as per Indian code. Or you may refer other codes. See, software will perform, that is not an issue. Software has the you can say option, you can just choose the value and you can, but the problem is what is the input we should provide, and what is the output we are expecting. That is what we need to understand. Obviously we are not going to do the analysis by hand, but the input and the expected output, we must have an idea about this, right? So that's why I'm not going to I have not covered this P delta thing here. Any other question? Now you can unmute yourself actually and you can ask the questions. I think. Yeah, Nishant, actually, let me 1 second. In YouTube, Nishant was saying that is it true that ETFs can properly calculate K values for small? See, there is doesn't matter it is G plus 1, G plus 2, or G plus 10. The calculation of K will be depending on the stiffness that is we are providing. Why does ETF shows very high reinforcement for G? See, the reason behind this high reinforcement is nothing but I think you are choosing the framing type as ductile. Now, when you are choosing the framing type as ductile, if you read IS 13920, there is this beam column capacity ratio, and it says the capacity of the column should be 1.4 times the capacity of your beams. Okay, so if your beams are having higher capacity, higher dimension, obviously the column needs to be 1.4 times its capacity. So this is the reason you will be getting higher reinforcement, and that is general. It is not a error of the software. It is what given in the code. Okay. Sarosh was saying, what is the last point in minimum eccentricity clause? Yeah, the last point was that whatever minimum eccentricity you calculated, PU into E, in that case, if it is less than 20 mm, then you need to consider at least 20 mm of eccentricity for the minimum eccentricity case. Yes, who was saying something? In Google Meet, someone is saying something, I guess. Hello? Yeah, yes. Tell me. Yes. Hmm. Hmm. Okay. No, we are not reducing the base shear value. Not at all. Hmm. No. Base shear. See, the thing is why we are considering this R, the you can say value. It is, yes, obviously the base shear will differ based on the R, because in the formula of finding the base shear AH we have this R thing. But the problem is here, this R we are considering depending on how much force you want to consider for the design of those frames, because you are eh, the total force for the 100% of force which is acting on your structure, you cannot design the structure for that 100% force. So some amount of force you need to allow to make damages in the structure, but that damage should not be a vertical failure. That is what our concept is in the seismic design. Okay, so if you are having, suppose, a amount of force, that 100% of a amount of force you cannot use for the design. So in that case, that force need to be reduced. So that reduced force will be used for the design of the structural elements, and the other forces will be allowed to make inelastic damages in the structure till it is not a vertical failure. So how it will be covering this? If you see the seismic resistant design, there are different criteria: ductility, redundancy, overstrength. So all these together will be, you can say, acting against that extra force that you have not considered for the design. Okay, so seismic design is different actually. So that is a huge topic. Even I am also not that much competent to explain this here. So yeah, any other question? Hmm. Yeah, that is what I'm saying now. In the seismic design concept, it is the same. In seismic design concept, you need more ductility rather than more strength. Okay, in the structure, you have to design the structure as more ductile. Okay, if you make the structure rigid, what will happen if it is not having enough ductility? What will happen? Like, you will see the sudden failures of the structures. Yeah, brittle failure of the structure. So this is in the seismic design concept. This is not there. maybe the structure will not be you can say useful after the seismic activity, but the structure should not fail during the seismic activity, or you must have enough time to evacuate the structure during the seismic activity. This is the whole concept, and even the same concept is applicable in any tall buildings also, whatever buildings are there, because life is more important than the investment that you have done in the structures. Okay. Inelastic, yes, ex- exactly. So, yes, exactly. This is what seismic design concept is actually. Some people is a seismic earthquake proof structure. There is no structure which is earthquake proof. Okay, there is no structure which is earthquake proof. The structures are earthquake resilient. Okay, seismic resilient it is, or seismic resistant. You cannot make a structure which is earthquake proof. Then your column sizes will be maybe for a G+1 structure, it can be 1000 by 1000 column, or maybe more than that. Okay, if you design the structure for whole force, total force. Okay, any other question? Yeah, thank you. Any other question? Anyone have? Okay, let me share one attendance link to all of you. I'll be sharing it in the YouTube also. So you will find it in the chat box, those who are using Google Meet. Okay, let me share it in the YouTube also. I think all of you can find the attendance link in the spreadsheet link. So I'll request all of you to you can say fill this attendance sheet so that we can send you the participation certificates. Vignesh Balaji saying, yeah, thank you so much. Actually, thank you so much for joining also. Anyone have any other question regarding this? Okay, so once you are done with the filling of the attendance form, then we will be closing our session today. Please let me know if everyone is done. So again, those who have not attended earlier, for your information, so we are available in two different platforms. One is the YouTube. All of you already know about it. So we have our YouTube channel, right? If you see here, so in this YouTube channel, we used to do this kind of activities, live sessions, recorded sessions. So almost 100 plus sessions are already available based on different topics, software programs and all. And then we have iOS and Android based platform. So those who are using Android, for them we have direct application of Illustraca Academy. If you find Illustraca in Play Store, you will find our app and you can register with your phone number and email ID. And those who are using iOS, you just have to follow two steps. You have to let me share the links with you so that you can easily find our platforms. So for YouTube, who are watching us on YouTube, it is already given in the comment box. And for those who have attended with Google Meet, I have sent the links actually for you in the chat box. So for iOS users, there is a application called My Institute. So you just have to download that My Institute application from App Store, and then once you open it, it will ask for a organization code. So you have to write the organization code as AMITCO, Amit Co, without any space. So if you see here, it is given here, Amit Co. So you can easily once you give it and log in, it will redirect you to our platform. So in our platform, there are different online courses available for structural designers, civil engineers. We have interview preparation course. We have site engineers course, which is very, if you see this site engineers course, it is very vastly you can say explained. If you see the contents, so number of contents are more than 200. So all the aspects of site engineering is covered here. You can see 126 videos newly uploaded. Okay, so it is vastly explained by engineer Akshay. So you can have a look on this. And another courses we have bridge engineers course, bridge engineering course, you can see, for the superstructure design of RCC bridges. Then we have the Stat Pro course and ETABS course, which is ongoing courses. Okay, so the Stat Pro course, the same kind of explanation will be there. All the detailed calculations will be explaining. Till now we have uploaded 9 videos on it. And for the ETABS course, if you see here, we have till now 40 sessions uploaded. So we have started the earthquake resistant design. Okay, so you can see this particular sessions also, and along with all the required documents, ETABS files, okay, AutoCAD files, so everything is given for you. Whatever we are using in the lectures, everything is given. All the lecture documents, that means whatever we are writing in our whiteboard during the lecture, it is uploaded here. So if you see here in our ETABS class, we have this lectures. So all these lectures are uploaded here. You can see up to 40 lectures we have. So all these lectures are uploaded for your ready reference. Whenever you want to, you will be referring the video, you can watch the PDFs also. And these PDFs and all these files are downloadable, but these videos are not downloadable. You will be having 1 year of access to this particular contents. Okay, so you can have a look. If you want to enroll to the course, you can. Otherwise, our YouTube is always available for you to this kind of contents that we are giving every day, right? So thanks for joining, all of you. It is really a pleasure to have all of you till the end. And those who are joining from YouTube, those who are joining from the Google Meet, thank you, all of you. We will see you in the next session tomorrow, the same time, and it will be on modal analysis concept. We will see how modal analysis is useful for the practicing engineers and how we'll be doing it. Okay, thank you. I think all of you are done with filling the attendance form. Anyone left? Okay, so we'll be closing today's session. We will see you tomorrow. Thank you again. Goodbye.